Hello, ECE 310 students. This is Dr. Vladimir Goncharov bringing you the video lecture for week 14, Monday, April 21st. In this lecture, I will cover difference equations, those that may be used to implement simple digital filtering functions. Also, digital filter network diagrams that may be implemented because they are causal. Also, implementing difference equation on the computer, and plotting digital filter frequency response in MATLAB. Let's begin with simple digital filters. A difference equation may be implemented using just a few terms to implement a low-pass filtering function. Here I show y of n as a function of present and past inputs. The present input is x of n. There's a one sample delayed input x of n minus 1. And also y of n is a function of past output yn minus 1. The scaling factor alpha may be adjusted in the range -1 to +1 to change the effective bandwidth of this low-pass filter. So taking the original difference equation, let's convert all terms to the frequency domain. In the frequency domain, the time delays by one sample are manifested by multiplication by e to the minus j omega. So now we may factor out terms and group them together to calculate the transfer function. Here we factored out y of e to the j omega from both sides and x of e to the j omega from the right side. And taking the ratio of these, we have the transfer function of the low-pass filter that I have presented to be the ratio of 1 plus e to the minus j omega divided by 1 minus alpha e to the minus j omega. Both numerator and denominator of this expression are functions of frequency. You will note that this matches the general form of transfer function for difference equations that are causal that was presented in the previous lecture. The general form shown here below for an mth order difference equation, in this case m is equal to 1, you only look back one sample in time, has the coefficients b sub k and a sub k defining the difference equation and hence defining the frequency transfer function. In this case, b0, that's a term that scales x of n, it's equal to 1. b1 is a term that had scaled x of n minus 1, that's also equal to 1. And that gives us a numerator expression, 1 plus e to the minus j omega. And then in the denominator, a0 is always equal to 1, that's that 1 plus term, followed by a summation of a sub k's. Because we have a1 equal to negative alpha, the second term subtracts from that 1. For example, let's take that same expression and assume that alpha is equal to 1/2. I'll show you later how to come up with this plot on the computer, but hand sketched is the magnitude transfer function of the low-pass filter defined by that difference equation. And what we're looking at is one period of a periodic spectrum, as must be the case, because all spectra corresponding to discrete time sequences are periodic. The period is always 2 pi, so it's enough to show the first period, that is the one centered at 0, going from -pi to +pi. Actually, if the difference equation has real valued coefficients, which this one does and most do that we are interested in using, then there will be this even symmetry about 0 in that period, so that actually we only need to show the range 0 to pi. But I just want to point out the periodicity by plotting both positive and negative frequencies. This spectrum peaks up at 4, so it actually has a gain factor of 4 at DC, at 0 frequency, and then it drops down to exactly 0 at pi and minus pi. And then in between there's a gradual transition. There is not a sudden transition as the ideal low-pass filter would have with a rectangular pulse that's centered at 0. In order to achieve that instantaneous transition, we would require m, the order of the filter, to be infinity. So that is why it is not realizable. And if we were to implement using computer programs or hardware, specialized hardware, the cost would be infinite. So this is an approximation to the ideal low-pass filter response. Similarly, we may look at the high-pass filter. Here is a simple difference equation requiring just a few additions, delays, and multiplication by alpha to implement. Again, the parameter alpha, which defines the edge of the stop band of this high-pass filter, may be varied in the range -1 to 1. And the coefficients B0, B1, and A1 are as specified to the right. M is equal to 1. This is only a first-order filter. You may think of M as the number of samples needed to look back in time in order to calculate the present time output. If M is higher, then we need more storage requirements to maintain a memory of past inputs and outputs. That's one way of looking at M. The higher the M, the more complex and costly this filter is to implement. So this is a simple high-pass filter, as was that low-pass filter. They differ in the sign of one coefficient, and that's the one in the numerator, the B1 term. But as a result of that, for the choice alpha equal -0.5, you will note that this periodic response that we had for the low-pass filter has shifted by pi radians per second to either left or the right to give us a peak at pi and 0 transfer function magnitude at DC. So this has the high-pass filter shape, looking over the range 0 to pi, where pi are high frequencies, the highest possible frequencies, and 0 is the lowest. You see that it attenuates low and boosts high, so it has a high-pass filter shape. The bandpass filter requires a higher order of difference equation to implement. With the bandpass filter, what we're trying to achieve is 0 transfer function magnitude at DC, 0 at pi, and then the peak somewhere in between. That peak will occur at omega naught, a parameter that is selected here as the argument of the cosine in the scaling factor to yn-1. Alpha is selected this time over the range 0 to 1 to affect the bandwidth of that peak, how narrow it is. And this simple second order difference equation then implements a bandpass filter response. The coefficients are given in order to put into the general form shown for H sub BPF. As an example, to demonstrate, I've chosen omega naught, the peak frequency, to be pi over 3 radians per second. So it's a third of the way towards the highest frequency possible. And then alpha, that parameter that adjusts the peakiness of the response, to be 0.8. By the way, if you choose alpha to be 0, there will be no peak. And then if you adjust alpha to be 1, the peak would be infinitely high and narrow, like an impulse. So somewhere in the range 0 to 1 will give you this control over the bandwidth of that peak. What's missing from this expression is a way of forcing the peak amplitude to be any particular value. That would complicate the expression, but it would only change the values of B0 and B1 by some scaling factor. I chose to leave those equal to 1 and minus 1 for simplicity's sake, which gives us a peak magnitude in the response of 5.56 approximately. So looking at this over the positive frequency range within one period, from 0 to pi, we see that it goes from 0 up to a peak value at omega naught and then back down to 0 at pi. This is the bandpass filter response, an approximation to the ideal, which would have been a rectangular pulse centered at omega naught. So, these difference equations may be implemented in hardware using building blocks of digital filters. And for that, it's very convenient to draw signal flow graphs, or we call them digital filter network diagrams. And we'll concentrate on the causal case, the case where delay units are used instead of something that is not realizable, the advance unit, which would presumably allow us to look into the future. Causal digital filter network diagrams form the blueprint for how specialized hardware may be designed and implemented in order to realize difference equations. These basic digital filter building blocks are the adder, the multiplier, but the multiplier does not multiply two sequences together. It simply multiplies by a constant, so it's a simple gain scaling operation. And the delay unit, which simply means taking a number, putting it into a storage location, and then retrieving it one sample later. Here's an example of a signal flow graph called the network diagram for a digital filter. The box following x of n stores that sample coming in and outputs it one sample later. So what's coming out will be x of n minus 1. That gets delayed again, passing into the second sample delay unit, so that its output would be x of n minus 2. Then those signals that are here noted in blue are scaled by constants b1 and b2 added together to give us y of n. This gives us a difference equation describing this network diagram. And so you see, if we could design hardware that implements a delay like that, and multiplication by a constant, and addition, we could implement this to convert one list of numbers into another list of numbers, one sequence x of n into another sequence y of n, to achieve filtering. Just as a circuit does that for analog signals, we can do it for sequences. And all of this may be related back to analog signals if what we started out with was an analog signal that was sampled to give us x of n. Now we can do a particular type of filtering. And then convert back to the analog domain by reconstructive filtering of the samples, and essentially duplicate or even perform types of filtering operations that are impossible in the continuous time domain. So this is a very powerful technique. Let's take a look on page 15 of the textbook on figure 611 at the nth order feedback network. Here is that figure, compressed a little bit to fit in the window available here. And what is feeding back? Well, y, the output, is delayed, multiplied by the scaling factors minus a1, minus a2, all the way up to the minus am, assuming this is an nth order filter. And those terms then add together with x of n to give us y. So this is a recursive definition of y, and all the delay unit outputs feed back in order to contribute to future signals. It's possible, therefore, that the impulse response of this network never dies down, continues some kind of non-zero output, even though the impulse response, the impulse at the input, x of n, had long gone. Because of this feedback, you can have non-zero values circulating in the loops without ever disappearing. In fact, that's what happens. Very rarely is it possible to apply an input signal so that those values circulating in the loops disappear and become zero. The corresponding difference equation to this feedback-only network is x of n minus a weighted sum of past outputs, giving us the present output. And if you take the Fourier transform of that, group the y e to the j omega terms and x e to the j omega terms and divide them to give the transfer function h e to the j omega, you will see that the frequency response has a denominator that has all those terms, and the numerator will be 1. Looking now at page 17 in figure 6.12, we have the discrete time feed-forward network. Notice here, what is delayed is not y, but rather x. The input is delayed, and those delayed samples of the input are fed forward to produce the output. They are fed forward by multiplying by the coefficients b0 through bm, and then all added together. X of n has no delay that gets scaled by b0. So what is different about this network is that once x of n disappears, that is, becomes 0 samples after some time, and it's a finite order filter, m is finite, eventually that pipeline of delays will produce zeros as well, and the output will become 0. M samples after x becomes 0, y will become 0, and there is no recirculation of values here. All the delayed values are fed forward. This will have a finite length impulse response, and its length will be m plus 1 points. So this forms a different class of filters called finite impulse response, whereas a previous feedback network was infinite impulse response. And that refers to the duration of that impulse response. Here, it's finite in length because there's no recirculation of values. The corresponding difference equation for the feed-forward case has only x terms in the summation, And the frequency response has the summation in the numerator and the denominator is equal to 1. So now we see that by combining the two of them, we can get the general case for any difference equation. Let's take a look at this general mth order discrete time network having both feedback and feed-forward paths. What you see here is a figure shown on page 20 of our textbook, figure 6.13, compressed slightly to fit on the slide. And it corresponds to the first block on the left half of this is a feedback network, and the right half is a feed-forward network. So it's as if we're passing the signal x of n through one filter that in the transfer function gives us a denominator summation of terms, and taking the output of that, passing it through another filter that in the transfer function gives us a numerator summation of terms to give us finally the output that we're looking for, y of n. An interesting thing is that we have these one sample delay units operating in parallel. They're storing the two vertical columns of delay units are essentially storing the same delayed samples, and in one case feeding them to the left and the other feeding them to the right. So they may be combined into a single chain. Here it is, and by saving that hardware, we now lower the cost of the filter. But otherwise, it is exactly the same as before. We have now a combination of two transfer functions being multiplied together. The difference equation is the one that was originally presented, defining difference equations on page 11 of the chapter 6 handout. And the corresponding frequency response is found by Fourier transforming both sides of that expression, grouping terms, and calculating the ratio of y to x in the frequency domain to give us transfer function shown here. This is the general case. Using this network diagram, we can implement any constant coefficient, and now these are called linear difference equation. Well, it's possible to design hardware that's dedicated to implement those difference equations. Just implement that network diagram directly. For delay units, you just have a shift register that stores values and shifts them on with each clock pulse. In a computer program, there is no dedicated hardware. We're using instructions to a computer that may be reprogrammed in order to process a list of numbers. What I show next is the pseudocode for a computer program that realizes the general case h of e to the j omega that was shown in the previous slide. Part of these comments are shifted off the screen. I apologize for that. But here it is in pseudocode. Now, pseudocode is kind of computer-like language. It may look like any programming language that you're used to seeing, but it's meant to put it in a form that no matter what language you're used to seeing, you'll understand it, yet close enough to computer language that you just change the syntax a little bit and you're able to realize it in your computer language of choice. So this is it for the general case, and you see it's really nothing special. Here we're able to write a simple computer algorithm with an infinite loop, by the way, where y of n is the output variable, and within each loop through this n is incremented, so we're producing updated values of y of n. What is not shown is how that y of n gets stored somewhere or outputted somewhere in order to give us the output. Finally, let's take a look at the plotting of digital filter frequency responses in MATLAB. All it is are these 3 lines of code. You're familiar with these because in the previous lecture we covered doing that for continuous time filters. W, which is my symbol for omega, is now defined to be linearly spaced, not logarithmically spaced, because of the periodicity of the frequency response. It's typically plotted on a linear frequency scale and over one period. So the period that I chose here is the one from minus pi to pi, and 1,000 sample points over that range, linearly spaced, are selected to form array W, omega. Then H, which here is implementing the transfer function 1 plus e to the minus j omega, divided by quantity 1 minus 1/2 e to the minus j omega, is calculated this way. Notice that the numerator is actually an array of points and the denominator another array of points, so they need to be divided a special way, dot slash instead of just slash. Oftentimes mistakes are made in MATLAB when we forget to do that. And now we've calculated 1,000 points of H, which are complex valued, so we take ABS before plotting them as a function of omega. And here's the result that we get in the figure window. Here we have duplication of the frequency response I had hand sketched for the first example in this video lecture. This is a low pass filter response. It peaks up at a value of 4 at 0 radians per second, and then at pi and minus pi it goes down to 0. This would be periodically repeating, but I only calculated it for one period, so here it appears as a single pulse. If you change the axis of the plot so that the minimum x value is 0, x coordinate, which is omega here, and the maximum is pi, and the minimum y coordinate is 0 and the maximum is 4, so those remain unchanged. But the important thing is I zoomed in on the positive frequencies omega 0 to pi. Now we're plotting frequency response of this digital filter, as is commonly done, over the positive frequencies only. And 3.14 is the highest frequency displayed, 0 is the minimum frequency displayed, and we're seeing a characteristic low-pass filter response. So, to summarize the main points of this lecture, it's very nice to know that low-order difference equations may be used to define simple digital filter types, such as the low-pass, high-pass, and bandpass filters. Using just a few operations, we may implement useful processing tasks that we typically define in the frequency domain as passing or blocking different ranges of frequency. We may implement these difference equations using either dedicated hardware, that is using adders, gain scalars, and delay units as described by the network diagram, or by using a general purpose computer as was shown using the pseudocode. The advantage of dedicated hardware is that it's usually faster and less complicated than the hardware that's needed in a general purpose computer, but a general purpose computer may be reprogrammed to implement any. In the network diagrams, we saw that we have both feedback and feed-forward paths, which leads to numerator and denominator terms in the transfer function. Later on, we will see that this contributes to poles and zeros in the transfer function in the Z domain. And finally, the higher the order of the filter M, the more delay units are required, the more multipliers and adders are required, so therefore the digital filter complexity increases. In this lecture, we looked at simple filters having order 1 and 2. So they were the simplest possible to achieve those desired characteristics. That's the end of lecture 14.1. Thank you for watching.